So welcome everyone. Today in this video, I would like to show you how do you unwrap a cylindrical geometry in ParaView into a rectangular seat-like geometry. And here we have a geometry here. Let's apply the geometry. So as you can see here, you have a cylindrical, not perfectly cylindrical, but it's a kind of stenos cylindrical geometry, as you can see. And what you intend to do is just we do not want to represent the data on the surface of the cylinder or the results on the surface of the cylinder. Rather, would like to unwrap the surface of the cylinder into a rectangular sheet. In this case, in this particular case, it would not be a perfect rectangular because we have a stenosis or constriction in between. But you got the gist. We just want to unwrap it, unfold it, the surface into a rectangle. And today I'm gonna show you how to do it. What I have found out is there are basically two ways to do it. One is very simple. We can use the calculator app here, which is here at the top corner, topmost left corner. And another is a bit advanced. We can use the programmable filter option, which is available in ParaView. Today in this video, I'm gonna show you how to do it using the calculator app. Since we are just interested in the results on the surface of the cylindrical structure, we will just make the surface active. That is, here you can see there are different parts of the geometry. We have the internal mesh, the wall, the inlet, outlets. Since we are just interested on the wall, we'll check only the wall. Let's say only the wall. And here we have the hollow wall. So this is our this is the geometry that we would like to unwrap. Let's say this is some results on the, it can be any result. This is some result on the surface of the cylinder, and would like to see it on a unwrapped surface. So we have this we have this cylindrical, let's say, okay, so we have this cylindrical geometry. Okay, and let's say we want to unfold from this particular point. What I mean to say is just concentrate on this particular circle. What you want to do is we just want to unfold from this particular area. So this is the next step, and finally when you completely unfold it, we'll get rectangle. I mean, this end will be this end, and this end will be this end. Okay, so if you extend the same thing to whole whole geometry, it will look something like this. Okay, a rectangular sheet. And what you want to do is this end should go in this particular example. You can do it any way you want, but in this particular example, what you want to do is this end should go to the top end, and it should lie in the positive y direction. Let's say, and this is the axis orientation here. This is x, which is along the axis of the cylinder. This is y, which is vertically top direction, and of course the z direction will come out of the screen. Okay, and what we intend to do is this rectangular sheet for this particular example should lie on the xy plane. That is, the coordinates for z will be 0. So let's write them. The coordinates of z will be 0 for the new sheet, rectangular sheet that we're gonna get. Then as you can already see, since we are unwrapping it in the and unwrapping it in the xy plane, the x coordinate of the surface of all the points on the surface of this cylinder will be same as the point, that corresponding point on the rectangular sheet. Isn't it? So because suppose this is a particular point, and when you unwrap it, let's say this point transforms to this point, and both this point will have the same x coordinate, right? So the x coordinate of the the new x coordinate will be same as the old x coordinate. So let's say x new is equal to the x old. Okay, and the tricky part is about the y coordinate of the points of the corresponding points uh, of the cylindrical surface. Okay, so for that, let's look at this particular cylinder. Let's look at this particular cylinder from the, you know, from from the towards the positive x direction, right? So it will look like this. Okay, so we have the z direction here, and we have the y-axis in this direction. Now what we're intending to do is we wanted to unwrap this point and bring it somewhere here. Okay, bring it somewhere here so that it just unfolds. Now the thing to look at here is, let's say we have this particular point on the surface, right? So how do we and how do we determine the y-axis of this particular point on the rectangular sheet? Okay, so for that we have to look at the coordinate. The coordinate here is y comma z. Okay, and this is the angle, let's say theta, and we'll do it what we'll do, uh, we'll just convert this is the arc length. Okay, this is the length of the arc from z to this particular point, from this axis to this particular point. We'll just assign this particular length to be the new y coordinate in the rectangular sheet. Okay, so how do you get this arc length? It's simple, right? In order to get any arc length in a cylinder, or in, let's say this is a circle, right? We have to multiply the angle theta in radian with the radius. Okay, so how do you get the angle theta? We can take the tan of theta is equal to y by z. So we have theta is equal to tan inverse of y by z. So this is the arctan, and radius. The radius will be simply the square root of the y coordinate, square root of the summation of the square of y coordinate and the z coordinate. So in simple sense, the new y coordinate of the new rectangular sheet will be the r into theta, basically. So this is y square plus z square into tan inverse y by z. So this is the transformation of the y coordinate from a point on the cylindrical surface to a point on the rectangular surface. But there is a there will be some inconsistency in here, because the tan inverse doesn't give you angle right from throughout the 360 degree. If you look at the graph, tan inverse, it looks something like this, right? So this corresponds to pi by 2, this corresponds to minus pi by 2, and this is of course the x direction. At infinity it reaches pi by 2, at minus infinity it reaches minus pi by 2. But in our cylinder, what we want to do, we want to assign this particular point, okay, just at positive 0 of z axis. we want to assign this particular point as plus pi, and a point which is just at the negative 0 of z coordinate. When the z coordinate is just the negative 0, we want to assign this particular point as minus pi and this particular point as plus pi. So that's what we want to do, and this won't be the case if we just use this simple formulation. We have to add something to this, and there is a very slight trick that you can do here. That is what I'm writing here now. But before that, let's look at what if you just use this particular formulation, what would be the value of the point, what will be the value of the y coordinate of the point at this particular point. Here we'll have a very y almost equal to r and z very small, that is almost 0. So tan theta would be positive infinity at this point. Okay, so positive infinity corresponds to pi by 2, right? So positive infinity corresponds to pi by 2. So this particular point will be pi by 2 in our present formulation. What we want to do is we want to add pi by 2 more so that it is pi. So let's add pi by 2 here. Okay, but at the same point, when we add pi by 2, if we look at this particular point, this is minus infinity, and minus infinity corresponds to minus pi by 2. Now if you uniformly add pi by 2 to the whole new coordinates of y-axis, this point would be corresponding to 0, right? This point would be correspond to 0, but we don't want that. What we want is, since this is minus pi by 2, we want to add one more minus pi by 2 such that it corresponds to minus pi. And a trick to that is we just have to do this. Just think about it. If we just do this, the whole stuff, fall into place. We'll add, whenever the z-axis is positive, we'll add pi by 2. Whenever the z-axis is negative, whenever the point lies on the negative side of the z-axis, we'll subtract minus pi by 2. Okay, so this is the new y coordinate that we'll have. This is the new x coordinate, which is simply the old x coordinate. Okay, and z is simply 0. So we just have to remember that, and we just put it in the calculator of the ParaView, and we'll see the new result. Let's do it. Let's open the calculator app. Here we have the calculator app, and before before going forward, just take the coordinate results option here. Okay, after that we just have to put the whole the formulation that we just derived in this particular blank space. Okay, before that, please don't forget to cross check this coordinate results. And what we have to basically put in this place is this particular expression. So this particular expression is nothing but what we have just written on the derived from the blank sheet actually. So I will just go through the expression once more. What it says is the coordinates, coords x means the coordinate x is the old x coordinate, is the new x coordinate, I hat is the I cap. So the new x coordinate is basically the same as the old x coordinate. And let's come to the last point. Here is the k hat, 0 k hat. This simply means the new coordinate, z coordinate will be simply 0, such that the new sheet that we just unwrap, it will lie in the xy plane. Of course, it's not necessary that you have to put 0 here. You can put anything. So it will just shift the rectangular sheet or the sheet that is formed of unwrapping the cylinder in that particular with that particular magnitude of value. It can shift in the negative also, and also in the positive direction, depending upon the magnitude, depending upon the value of what you put before the k hat. And in between them lies this huge expression, and this expression is nothing but so let's see what it exactly is. So this portion, if you see it, this is nothing but the square root of y square plus h square. This is the radius. Okay, so radius into theta, and this whole expression basically represents theta. This is the multiplication of the radius, and this whole expression represents theta. How? This is the a10 is tan inverse of coordinate of y by coordinate of z. Okay, so and we already discussed that how it doesn't exactly do our job, so we have to somehow improvise something. So this is the improvisation part, where we add pi by 2. So this value is nothing but this is the value of pi by 2 in radian, and we just multiply with it coordinate of z by the absolute value of coordinate of z. So we just copy it here, and put it here in this space of the calculator, paste, and just apply. And here we have the cylinder unwrapped in front of us. Okay, so we can view both the cylinder and also the unwrapped surface together if we just activate it. So this was the original surface. Okay, and we have unwrapped it into a sheet. Okay, so that's all for today. Hope this video helped you. Thank you.